What's up, everybody, and welcome back to another video on SAT Math from the Scalar Learning channel. This is one that a lot of students have asked for, and it is all about the must-know geometry and trig on the SAT. Let's do it. And real quick, before we get started, if you are interested in tutoring, hit us up at tutoring@scalarlearning.com. And if you're interested in buying our SAT Math video course, which is amazing, it's got 4 practice tests of math only and video explanations for every single one of those problems. You can get it in the description link below. It's only $15 a month, and you can cancel it anytime, so you can literally buy it now, study, cancel, and be done. So the first thing we want to talk about is the SAT reference sheet. This is something that is given on both the calculator and the no calculator section. So here's the reference sheet, and you want to be familiar with what's on it. We've got circle, area, and circumference. We've got area of a rectangle, area of a triangle, Pythagorean's theorem, and special right triangles, both of which I'm still going to go over because I want to explain conceptually how to approach them and apply them. We got a volume of a rectangular prism. I'm going to talk about volume of a potential triangular prism, which has been coming up a lot lately. We've also got a volume of a cylinder, volume of a sphere, volume of a cone, and on the bottom right is the volume of a pyramid. They also tell you, which is very important, the number of degrees in the arc of a circle and the number of radians. Now, degrees and radians are 2 different ways to measure the same thing, but that right there tells you the equivalency. 2 pi is 360 degrees, or 1 pi radian is 180 degrees. And then the last thing they tell you is the triangle sum theorem. Again, I'm going to go over that as well with a visual to explain it better, but they say, oh, all the angles in a triangle add up to 180 degrees. So first, we're going to talk about some common shapes that you should be aware of and just understand what the terminology means. So for example, here in the upper left-hand corner, we have a quadrilateral that's a kite with these 2 sides up there congruent, 2 sides on the bottom congruent, and it looks essentially like a kite. That's why it's called a kite. Now, these aren't that commonly tested, but just so you know the terminology. Then we have a parallelogram. These show up all the time. The opposite sides are parallel, right? And then we have a trapezoid, and I have recently seen a trapezoid area question, which we're going to go over that formula as well later on. Rectangle, pretty common. Square, pretty common. A rhombus has 4 congruent sides. Also, the opposite angles are congruent. Then on the bottom, we've got a right triangle. That's a triangle with 1 right angle. An isosceles triangle, that's at least 2 congruent sides. So here we have those 2 sides on the top that are congruent, but you theoretically could have all 3 sides congruent, and it's still technically an isosceles triangle. Finally, on the bottom, that's an equilateral triangle where all 3 sides are congruent. So I just want to also go over some angle measures that are important with some of these shapes. So for example, in a parallelogram, you see that the opposite angles are congruent. So that's just something that's not a bad thing to know. Also, we can see down here in the isosceles triangle at the bottom in blue, those 2 opposite angles of the congruent sides are also congruent. That's the isosceles triangle theorem. Conversely, if you know that those bottom 2 angles are congruent, you know that the opposite sides are congruent. So that's a good thing to remember. And in the equilateral triangle, all 3 angles are congruent. And that also means, since all the angles add up to 180, that all 3 angles equal 60 degrees. Next, we're going to talk about some 3D formulas that aren't necessarily on the reference sheet. So here we're going to talk about prisms. Now, they do have it for a rectangular prism, length times width times height. But what if you get a triangular prism or some other shape that is a prism? And again, a prism is just one shape that's sort of extended backwards. In the second image here, it's a triangle that's extended by that height value. So we've got a triangular and a rectangular prism. The volume is simply the area of the base. So whatever is that shape that's being extended back, you calculate the area of that, and then you multiply it by the height. So that doesn't matter if it's rectangular, triangular, or whatever. You just have to get that area of the base. Now we talk about surface area of a prism. So again, the surface area is the area of every single face. So you see with that rectangular prism, we have 6 faces, right? With that triangular prism, we only have 5 faces. So the way to calculate this is basically if you take the perimeter of that base, you multiply it by the height, and then you add 2 times the area of the base. Regardless of the type of prism, this will work. The reason why I bring this up is because I've seen these surface area questions lately popping up on recent SATs, but I do want to remind you that if you have trouble memorizing that formula, just always go back to being like, well, okay, this is a prism. It has a certain number of faces. I can count those number of faces. Then I can look at each face as a single 2-dimensional shape, calculate the area of each face, add them up, boom, done. Now we're going to talk about a couple area formulas that I've seen pop up lately that aren't on the reference sheet, right? So first we have a parallelogram. Parallelogram, once again, the two opposite sides are parallel, and the area is simply base times height. Now you can also break this up into two triangles and a rectangle and do it that way, but that's it. It's a very straightforward formula, the base times the height. The other one that I've seen recently is a trapezoid. So it's the bases are those two sides that are parallel. So you take the average of base 1 and base 2, and then you multiply it against the height. Again, if you forget this formula, you can break a trapezoid up into two triangles and a rectangle if enough information is given, and take it from there. But this is the official formula. Next, we're going to talk about the triangle sum theorem. Again, this is provided in the front on the reference sheet, but here it is visually explained. So we got a triangle, we got three angles, and the three angles added up are always 180 degrees. Next, we're going to talk about Pythagorean's theorem, which again is also on the reference sheet, but let's see how it works in a couple examples. So this is the famous a squared plus b squared equals c squared, where a, b, and c are the side lengths of a right triangle. And the most important piece is that c has to be the hypotenuse, meaning it's opposite that right angle. And if you visualize this, we're squaring each of those sides. So it's almost like we're turning them into squares, and the area of square A plus the area of square B down in the left equals the area of square C. A numerical example could be 3, 4, and 5. So these are actual values of a potential right triangle. If you square them, you get 9 plus 16, which indeed equals 25. Now we're going to see Pythagorean's theorem in action, where we're going to actually solve for missing sides. So say, for example, we have a right triangle here with one of the legs as 5, one of the legs as 12, and we've got an unknown hypotenuse. So the way we would solve for the hypotenuse is we plug it into the formula. 5 squared plus 12 squared equals c squared. Now again, which one you designate as a and b doesn't matter. C, it just has to be the hypotenuse. So 5 squared is 25, 12 squared is 144. We add them up, we get 169. Then we take the square root of both sides, and we get c equals 13. Boom, done. Here's another example where we're going to be trying to find a missing leg. So we know that 7 is one leg. We know that the hypotenuse is 25. So what is b? So let's plug it into the theorem. We have 7 squared plus b squared equals 25 squared. 7 squared is, of course, 49. 25 squared, excuse me, is 625. So then we're going to subtract 49 from both sides. We get b squared equals 576. Then we take the square root of both sides, and we get 24. Boom, done. Now we're going to talk about special right triangles. Again, these are on the reference sheet, but I want to talk through both of them because they're very important. They come up in a lot of questions. So here we have our 45, 45, 90. And on the legs, the sides opposite the 45-degree angles, we call those x. Sometimes you call them 1. It doesn't matter. And the main key is that if those are x, the hypotenuse is whatever that x value is times the square root of 2. For 30, 60, 90, this is the other common special right triangle. We've got the opposite side of the 30 degrees as x, opposite the 60 as whatever that x value is times the square root of 3, and then the hypotenuse is 2x. One way to remember that is it is a 1, 2, 3. If you think about it, the little leg is 1, the hypotenuse is 2, and the big leg is 3, radical 3, but still 3. So now we're going to take an example of a 45, 45, 90 and show you how you can find the missing side lengths when you have 1 or 2 or whatever. So here we have 3 as the legs. So you see 3 matches up with the legs, and therefore that hypotenuse is going to be 3 rad 2, and that matches up with that hypotenuse. Now let's look at a 30, 60, 90. Here we have a 30, 60, 90 with 6 as the little leg. That means since 6 is our x value, that our larger leg is going to be 6 rad 3. So now those two match up. And then we go back to the little leg to get the hypotenuse. We double it, and we get 12 as the hypotenuse, which matches up with 2x. Now we're going to talk generally about polygons and some basic definitions. So first of all, what does congruent mean? Congruent means identical. So two shapes are congruent if they are the exact same, meaning they all have the same side lengths and angle measures. Another example here with this octagon, those are congruent. They're exactly the same. Next, we're going to talk about similarity. Similarity is like it's the same shape, but one is bigger or smaller, aka proportionate. So for example, we have this nice little pentagon, and it is similar to this pentagon. So you see the sides are bigger, but all the angles are the same. It's literally blown up or enlarged. Another example is, again, this octagon. is similar or proportionate to this little octagon. So just to recap, the sides are proportionate, meaning for the blue pentagon, if all the sides are 2, 2, 2, 2, 2, maybe for the larger one, they'd all be 4, 4, 4, 4, 4, double, right? So that's the proportion. And all the angles, again, are congruent. So similar, angles are congruent, sides are proportionate. Now we get into some really important stuff because we've been seeing a lot of proof-like questions. Which of the conditions are sufficient to prove that these triangles are congruent? Which of the conditions are sufficient to prove that these triangles are proportionate? It all comes down to the theorems I'm about to show you. So I would highly recommend memorizing these theorems. So to prove two triangles are congruent, first we have the side, side, side theorem, meaning if all three sides of two triangles are congruent, the triangles have to be congruent, meaning everything matches, not only the sides, but the angles as well. We also have SAS, side, angle, side. Now this is very important to note that it's not just two sides and a random angle. The angle has to be nestled in between those two congruent sides in that exact order to prove congruence. We've also got angle, side, angle. Once again, the same thing is true. That side that's congruent has to be nestled in between those two congruent angles. And again, those two congruent angles are, of course, adjacent, right? And then we have an angle, a side, and angle. Then we have angle, angle, side. So this one's a little bit more chill. As long as we got two angles and then another side congruent in two triangles, we're good to go. It is important that that congruent side is opposite the same angle in both of those triangles. But there you have angle, angle, side. And last but not least, hypotenuse, leg. This is a situation where if we know the triangles are right, meaning they both have a right angle, we've got the hypotenuses lining up, one leg lining up, you're good to go. They're congruent. And now let's talk about the similarity theorems to prove triangles are similar. So we have three. First is angle, angle. This is the most commonly tested one. If you can show that two angles in any two triangles are congruent, then the triangles have to be similar, aka proportionate. Then we have side, angle, side. If I can show that two angles are congruent and then I have sides on the outside being proportionate, you see, AB over XY, right, those are the proportionate sides next to those congruent angles, is the same as AC to XZ, the other sides that are next to the angle as well. And if you have proportionate sides, angle, proportionate sides, they must be similar. Last but not least, we have side, side, side. But again, this is not side, side, side congruence. This is side, side, side similarity, meaning all three sides have to have the same proportion. Next, we're going to talk about the interior angles of polygons. So the cool thing is that you can get the sum of the interior angles of any polygon by applying this formula, n minus 2 times 180. And that n, of course, is the number of sides of the polygon. And now we're going to go through some examples to check it out. So if we have a triangle, we all know that it adds up to 180 degrees, but you can also plug it into this formula. 3 minus 2 is 1 times 180 is 180. And for a quadrilateral, it's going to be 360. Now, the rest of these examples are not nearly as likely to be tested, but you can see how it's calculated. And by the way, the angle measure on the far right-hand side is assuming these are regular shapes, right? So if they're regular, all the angles and sides are equal. So I'm just basically taking that angle sum and dividing it by the number of sides. Next, we're going to talk about the exterior angles of polygons. Now, this isn't as commonly tested at all on the SAT, very rarely, in fact, but I figured I'd throw it in just in case. But it's pretty cool because for any polygon, the sum of the exterior angles is always 360. It's beautiful. So check this out. If we have a pentagon, this is regular, of course, so all the angles and sides are equal, but every angle is 72 degrees. Guess what? That adds up to 360. Also, in a hexagon, then the exterior angles would all be 60. Once again, they're adding up to 360. Next, I want to talk about angles, but in particular, the relationship between degrees and radians. So once again, they put this on the reference sheet. 360 degrees is equivalent to 2 pi. But just so you have some idea in terms of some other equivalent values, I thought I'd go down the list. So check it out. 0 is, of course, 0. 30 degrees is pi 6. 45 is pi fourths, okay? So, and to do the conversion, I'm going to show you in a second, there's a formula you can apply, but just to see some equivalencies, 60 is pi thirds. 90, that's an important one. That's pi over 2. And that makes sense because 2 pi is 360. And then we've got a few more that are very important. But the most important is 180 degrees equals pi. Now to do the conversion, if you're going from degrees to radians, you take your degree value and you multiply it by that relationship, by pi over 180, because again, they're equivalent. If you go the other way from radians to degrees, you multiply it by the reciprocal 180 over pi. Next, I want to talk about some relationships involving angles. So we want to know the terminology of complements, which are two angles that add up to 90. So you can see, for example, here, if we got a right angle, we break it up into two angles. X and Y would be complements. So examples would be 15 and 75 adds to 90. 30 and 60 adds to 90, etc. Also, I want to talk about supplemental angles. Supplements are angles that add to 180. So, for example, here we have a straight angle, and we got those two linear pairs, W and Z. W and Z, if you add them together, add to 180. Two examples would be 30 and 150, and 95 and 85. Another thing that's very important is to understand the rules surrounding parallel lines. So if we already know that these lines are parallel and we draw a line through it, meaning a transversal, we have some angle relationships. The angle relationships are as follows. So first we have corresponding angles. What are corresponding angles? It's kind of like if you take an angle and you slide it up the transversal and it goes up to that next parallel line, it looks like the exact same angle. Those are going to be congruent. So for example, we have 2, if you slide it down, will be the same as 6. 4, if you slide it down, will be the same as 8. Likewise, we have 1 is congruent to 5, 3 is congruent to 7. We also have alternate interior angles, meaning on the inside of those parallel lines. So we have alternate, meaning 4 and 5, they're kind of on the alternate sides of the transversal, but they're congruent. They look congruent, so that makes sense. We also have 3 and 6. Next, we need to know that alternate exterior angles are congruent. Those examples would be on the outsides of those parallel lines, like 1 and 8 and 2 and 7. We also have consecutive interior angles. Consecutive interior angles would be on the insides, but on the same side of the transversal. Now, that would be like 4 and 6, but they're not congruent. They are supplementary, and it's important to remember that they add to 180. Likewise, we have 3 and 5 add to 180 as well. For all of these relationships, yes, it's important to know that if you have two parallel lines, these relationships will exist. But equally as important as that is that the converse of this is true. So for example, if I have two lines and I don't know if they're parallel, but I'm trying to figure out or prove that they're parallel. If I know that any of these things are true, that's enough to prove it. If I can show that a pair of consecutive interior angles are supplementary, parallel. If I can show that a pair of alternate exterior angles are congruent, parallel. Alternate interior angles are congruent. And just one, that's it. Parallel. Last but not least, corresponding angles, congruent, parallel. So it's very important. I've been seeing those a lot lately in the last 2 years. Finally, we do want to be aware that vertical angles are congruent, but that has nothing to do with whether or not these lines are parallel. So vertical angles are kind of like on the other sides of each other in that X formation. So for example, we have 1 and 4. They're sort of across from each other. 2 and 3, 5 and 8, and 6 and 7. Next, we're going to talk about trigonometry, and the most important thing in trigonometry to know for the SAT is SOHCAHTOA. So SOHCAHTOA is sine, cosine, tangent, but those OHAHOA values are very important because for sine, it's opposite over hypotenuse. What does that mean? If our angle is A, sine of A is the ratio of the opposite side of A to the hypotenuse, which is always going to be opposite the right angle in green. Cosine is adjacent over hypotenuse. So this is the adjacent side of A in brown over the hypotenuse once again in green. And again, this is relative to A. It would be a different value if we were using a different angle in the triangle. Last but not least, TOA, opposite over adjacent. So that would be, again, the blue over that brown color. Again, that's relative to A. So now let's tackle some problems involving SOHCAHTOA. So let's say we have a triangle here, and there's our theta. That's the angle that we're using in these calculations. Again, it's arbitrary, but it will be designated based on what the College Board designates. Now, let's say we have a 5, 12, 13, and I want to know what is sine of theta? Well, it's opposite theta, which is 5, over the hypotenuse, which is 13. What is cosine of theta? That is adjacent next to theta, which is 12 over 13. And you might say, well, wait a minute. 13 is also adjacent to theta. That's true, but we're taking the non-hypotenuse adjacent side. So that's 12 in this case, the leg over 13. Last but not least, tangent, TOA, opposite over adjacent, which is 5 over 12. Just an aside, sine and cosine will never be greater than 1 or less than -1, whereas tangent, you could have something greater than 1 or less than -1. Another very important rule to remember, sine of x equals cosine of the complement. So just some quick examples because they test this all the time. It's a lovely shortcut if you remember it. Sine of 10 is the same as cosine of 80. 30 is the same as cosine of 60. Sine of 45 and cosine of 45 are equivalent because 45 and 45 are complementary. So that's just some good stuff to remember because they do like to test it. You can still figure it out other ways, but it's a nice shortcut. Now I want to talk about the sign, aka positive or negative, of all the trigonometric functions, depending on what quadrant an angle appears. So we have quadrant 1, 2, 3, and 4. And the sine and cosine and tangent values will have different signs depending on which quadrant we're in. So just to give you an idea, and this kind of goes back to the unit circle, quadrant 1 are all the theta values between 0 and 90, or 0 and pi halves, depending if you're in degrees or radians. 2 would be 180 to 90 and pi halves to pi. 3 would be 180 to 270 or pi to 3 pi halves. And 4 is 270 to 360 or 3 pi halves to 2 pi. So now I'm going to give you a way to remember what's what. So check this out. All students take calculus. So what does that mean? That means that in quadrant 1, everything is positive. Sine, cosine, tangent. That's all you need to know. In quadrant 2, only sine is positive. That's the S, students, right? If you take cosine or tangent in quadrant 2, it will be negative. Take T, that's tangent. Tangent is positive in quadrant 3. Last but not least, and by the way, the other two are negative, right? Sine and cosine are negative in quadrant 3. Last but not least, calculus, quadrant 4, that's cosine. So cosine is positive in quadrant 4, but the other two will be negative. So now let's take some examples. If I took sine of 120 degrees, that would land us in quadrant 2. That result would be positive. If I took sine of 195, now we're in quadrant 3, right? So that means sine will be negative in quadrant 3. If I took tangent of 220, that lands us in quadrant 3 where tangent is positive. Tangent of 330, now we're in quadrant 4, it's negative. Last but not least, cosine of 335, quadrant 4, positive. Cosine of 135, now we're in quadrant 2, that is negative. The last thing I want to show you for trigonometry is the unit circle. Now, in the past, I haven't really talked about the unit circle because I felt like it wasn't necessary to memorize. I still feel that way, but it has come in handy on some of the recent tests for some of the particular questions where they basically straight up ask you a question that if you remember the unit circle, you can instantly answer it. So I'm going to go over it today, but I want to talk about a way to memorize it really, really efficiently. And again, if you have trouble, I wouldn't stress. There's ways around it. But here is the unit circle. This is a unit circle that I made, and I just updated it. It's color-coded, and there's a reason for the color coding. So you look at it, and you're like, man, there's so many values, I can't do it. But look at the reds. They repeat all the way around, just with different signs. And the way you apply the signs makes sense based on the quadrants. For example, in quadrant 2, in red, the x value is negative. Well, that makes sense. In quadrant 2, x values are negative, y values are positive. Quadrant 3, everything's negative. Quadrant 4, just the y value and the x value is positive. So if you remember the red, blue, and green pairs, you can simply apply them around the circle in this order and then put the signs on after the fact just based on, oh, this one's positive, this one's negative in this quadrant, whatever. The coordinates in black are a lot easier to remember because this is a unit circle. It's got a radius of 1. So you go out to the right, it's 1, right, for x, but the y is 0. You go straight up, it's 1 for the y, but the x is 0, and so on and so forth. The other cool thing to remember is that sine of any angle in the unit circle is equivalent to the y value of the related coordinate in the unit circle. Cosine relates to x, and tangent relates to the ratio of y over x for that angle measure. So just to give you some examples, sine of 45, check it out. That's a blue value. You look at 45 degrees. I take the rad 2 over 2 from the y value of that particular coordinate, and that's where I get my answer. Boom, done. Let's say we've got cosine of 150. So I look at 150. And it's got a coordinate there. Since cosine represents the x value, I know it's negative rad 3 over 2, and I'm pulling it from that value on the left. Boom, done. Last but not least, tangent of 240. Now I'm saying that's rad 3. Well, I don't see rad 3 as a value. That's because tangent of 240 is the ratio or fraction of the y value of that coordinate over that x value. So negative rad 3 over 2 divided by negative 1/2 is simply rad 3. Next, let's talk about circles. Again, these formulas are on the reference sheet, but you should know how to apply them. The circumference is that radius from the center to the outside times 2 pi. Area is pi times the radius squared. Now, here are two formulas that are not on the reference sheet, but that are related that you should know. First is arc length. So you'll notice arc length, it's like a piece of the circumference. How do we get that piece? We take the circumference and we multiply it by the central angle out of 360. Why out of 360? Because that's all the degrees in a circle. So it's the part over the whole. If this were in radians, it would just be that central angle over 2 pi, because 2 pi is the same as 360. Next, we have area of a sector. That's like a pizza slice, right? So it's again a piece of the area. It's the same exact principle. We take the area of the circle pi r squared and we multiply it by that central angle over 360. Next, I want to talk about arc measure. So that is the measure of an arc, but that is going to be in degrees or radians. So that's the first thing, that it can be in either of those. You can also have arc length, which is, we just talked about. That's not in degrees or radians. That's going to be an actual length measure. So it's a little bit different. It's equivalent to the central angle that kind of cuts it out. And I'm going to show you what that means in a second with an illustration. And if we have an inscribed angle, it's going to be double the inscribed angle. So all this doesn't make a lot of sense until we see it. So I'm going to show you what it looks like. So if we have a circle here, we have O at the center, and we have this arc. So the measure of that arc is going to be the same as the central angle. So that central angle is AOB is 50. Therefore, the measure of that arc is also 50 degrees. Now in this second circle, we're going to have that same arc measure AB, but now we're coming from C. This is an inscribed angle because it's coming from the actual circle, not from the center. So in this case, if we have the same arc measure of 50, that central angle ACB is going to be half of the arc measure. So it's going to be 25 degrees, or the other way to think about it, arc measure is double that inscribed angle. Next, we're going to talk about the circle equation. You've got to know this equation. It always shows up. So check it out. It's x minus h squared plus y minus k squared equals r squared, where the center is h comma k. So notice, if it's a center at positive 3, positive 4, it's going to be minus 3, minus 4. And then that r value is, of course, the radius. So just for illustration purposes, here we have the center, h comma k, and the radius is that length from the center to the outside. So now let's take an example with the circle equation. So let's say we have this equation. Well, guess what? It's not in the right format. So you may, on hard circle problems, have to put it in the right format. So how do we do that? We're going to do this by completing the square for both the x's and the y's. So check this out. We're going to rewrite it. We're going to break it up. It's all grouped together nicely. So how do I complete the square? Well, I've got x squared plus 4x. I take that 4x term, the b term, and I divide 4 by 2, and I get 2, and I square that. So that means I'm going to add 4 to that value. But I can't just add 4 to the left side. I must also add 4 to the right side to keep it balanced. Now I'm going to do the same thing with that negative 8, right? So negative 8, half of that is negative 4. If we square that, it's 16. So now I'm going to add 16 to the left side as well as the right side. So now we're going to come down here, and that is a perfect square trinomial. I'm going to factor it as such. So is this as well, and we're going to factor it as such. So on the left, we get x plus 2 times x plus 2. That's what we want. And for the y's, we get y minus 4 times y minus 4. And on the right-hand side of the equation, we add everything together, and we get 9. Beautiful. Now I'm going to rewrite it one more time, because x plus 2 times x plus 2 is the same as x plus 2 squared. Y minus 4 squared can be written as that, and now we have equals 9. Now we're in the standard form. Now I can tell you what each of the components are. Now I can tell you that the center is at negative 2 comma 4, because again, it's the opposite, right? It's not positive 2, it's the opposite, which is negative 2. And the radius is the square root of 9, which is 3. All right, guys, that is it for all of the must-know geometry and trig on the SAT. I hope you found it useful. I hope you found it helpful. I definitely recommend to study this material as much as possible before going in on test day. If you like this video, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.